What if I told you that right now time is passing at different speeds across our planet and
If you are standing on a beach, your clock is ticking ever so slightly slower than someone standing directly on top of Mount Everest. The difference is incredibly small, far too small for you to notice, yet with modern atomic clocks we can measure it with absolute certainty. Time is not flowing equally everywhere, as we discovered that high speeds change the passage of time for astronauts and satellites alike. But motion is only half the story. As Einstein himself realized, there was something even stranger hiding beneath the surface of reality. If speed could change time, could gravity do the exact same thing, forcing him to completely rewrite our foundational physics? Because gravity is not simply a force pulling objects together, it is something far more profound, bending the fabric of reality itself. To understand how he reached this conclusion, we must travel back to one seemingly ordinary morning in 1907, at his desk. Newton had explained gravity with remarkable success, stating that every object with mass attracts every other object in an orderly universe. But Einstein was bothered by one question: how does gravity actually communicate its presence instantaneously across empty space? Then came the thought that he would describe as the happiest idea of his life, involving a man falling freely from a building roof. Surprisingly, he would feel completely weightless as his keys and coins would float right beside him in that tiny falling world. Now imagine a sealed elevator accelerating upward in deep space, completely isolated from every planet and every star. Without looking outside, they cannot tell whether they are standing on Earth or accelerating rapidly through the empty cosmic void. This simple observation became known as the equivalence principle, showing that gravity and acceleration are fundamentally connected. If they are the same phenomenon, perhaps objects are not being pulled, but are simply following the natural geometry of spacetime. Imagine stretching a large rubber sheet tightly across a frame and placing a heavy bowling ball directly in the center. When you roll a marble across the surface, it curves toward the center, simply following the distorted shape of the path itself. Mass tells spacetime how to curve, and curved spacetime tells matter exactly how it must move throughout the universe. Planets are not being pulled around the sun by invisible strings, they travel along the straightest possible paths in curved space. If space can curve and time is an inseparable part of spacetime, then time itself must curve as well. Near massive objects, near massive concentrations of mass, time should pass significantly slower, not because of broken clocks but due to reality changing. Nothing in ordinary experience suggested that gravity could influence time, yet Einstein's equations insisted that it must happen. During the middle of the 20th century, physicists began developing instruments of unprecedented precision, atomic clocks. If he was right, identical clocks placed at different heights above Earth should slowly but surely drift apart over time. Before atomic clocks would settle the question, another elegant experiment would provide the first direct glimpse of gravity's influence.
In 1959, two physicists at Harvard University named Robert Pound and Glenn Rebka designed a historic test.
Imagine standing at the bottom of a tall building and shining a beam of pure light straight upward towards someone on the roof. As the light climbs away from Earth's gravity, it loses energy, stretching its wavelength in a phenomenon called gravitational redshift. They used gamma rays emitted by radioactive iron atoms, which possess extremely precise frequencies ideal for detecting shifts. After months of careful measurements, the result became clear, as the gamma rays had the exact frequency shift predicted by Einstein. Over the following decades, technology advanced and modern optical lattice clocks became stable enough to observe relativity in labs. With every step upward, you take, gravity weakens slightly, and your personal timeline begins running ever so slightly faster. Orbiting more than 20,000 kilometers above Earth, GPS satellites reside where gravity is significantly weaker than the surface. According to general relativity, weaker gravity allows their onboard clocks to run faster by about 45 microseconds each day. If engineers ignored these corrections, GPS positions would drift by roughly 10 kilometers every day, making the system useless. But Earth is a gentle place with weak gravity, while the universe contains extreme objects whose mass dwarfs our planet entirely. There exists a place where gravity becomes so overwhelming that spacetime folds inward, creating the ultimate time machine, the black hole.
Every star in the night sky is fighting a constant battle between gravity crushing inward and nuclear fusion pushing outward.
When the nuclear fuel finally runs out for a massive star, gravity wins, instantly causing the core to collapse in a supernova explosion. If the remaining core contains too much mass, no known force can stop the collapse as the star shrinks further until a black hole is born. As you get too close, the side of your body nearer to the void experiences a much stronger pull, causing an effect called spaghettification. Which brings us to one of the most mysterious boundaries in the entire cosmos, the completely invisible event horizon. Once anything crosses this boundary, escape becomes impossible, because every single path through space-time leads directly inward. Imagine watching an astronaut slowly descend toward the edge as gravity intensifies. Their clock runs slower relative to yours. To your eyes, they appear to slow almost to a complete stop, at the very edge, fading gradually into absolute darkness. This extraordinary idea entered popular culture through the film Interstellar, where 1 hour on a planet equaled 7 years on Earth. The filmmakers worked closely with physicist Kip Thorne, ensuring that the visual effects were built directly upon Einstein's equations. But could space-time bend so dramatically that it connects two distant regions, creating shortcuts across billions of light years?
The mathematics suggests that such objects might actually exist in our universe, and they are known to science as wormholes.
Imagine taking a simple sheet of paper, drawing two dots on opposite sides and folding it until the dots touch directly. To keep a wormhole open, physicists believe it would require exotic matter possessing negative energy density to resist collapse. If a stable wormhole could exist, you might emerge at a completely different point in time, leading to closed timelike curves. A closed timelike curve is a theoretical path through space-time that eventually loops back directly to an earlier moment in history. Because the moment we imagine traveling into the past, paradoxes immediately appear, such as the famous grandfather paradox. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics may actively prevent time machines from forming. Some physicists began asking an even more unsettling question: what if the forward flow of time itself is merely an illusion? This idea is known as the block universe, where the past, present, and future all exist simultaneously, like slices of a loaf of bread. From this perspective, time does not flow. Instead, we flow through time as our conscious minds move along our personal paths. More than a century later, many predictions have been confirmed, including gravitational waves produced by massive colliding black holes. Yet enormous mysteries remain as scientists try to unite relativity and quantum mechanics into a single theory of quantum gravity. We can measure it with astonishing precision, yet we still do not fully know why time exists in the specific form we experience. Somewhere another young scientist may already be asking the simple question that changes our entire worldview all over again. The universe has taught us that time is not fixed. It bends, it stretches, it slows, shaping every star and every human life.
Every time we believe we finally understand the universe, it reveals an even deeper mystery waiting just beyond the cosmic horizon.